Hi, hello everyone. This is your educator, your tutor, your friend Sanjay Vishwakarma. I welcome you all to yet another session of We Learning. We Learning is a platform which focuses on providing right to quality education for all. Do watch this session. If you like it, do press the like button and share it with your other friends who are preparing for their boards and competition as well. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. Alright? Do visit our website also www.we-learning.in. You will be getting all these live sessions there. Along with that, you will be getting lecture notes in PDF format. You can learn from them. Okay, so do check it out. Now, without any delay, let's get started with today's session. We were doing moving charges and magnetism, and this is lecture number 9. In this lecture, we are going to talk about force between parallel infinite current carrying conductors. When two current carrying conductors are kept, current is flowing in that, then what is the force experienced by each of the conductors? And then we will be seeing the definition of Ampere. From this only we will derive the definition of Ampere. Okay. Then we will be seeing torque on a rectangular current loop in a uniform magnetic field. We have already seen in a uniform magnetic field, if a current carrying conductor is there, it experiences force. F is equal to IBL sin theta, right? Now here we will be seeing the force also and the torque also if it is a loop. Clear? Alright, let's begin. So force between parallel infinite current carrying conductors. So suppose there are two infinite wires. This infinity sign means it's a very long wire. Both the wires are very long. Okay. Or you can assume these two are kept near each other. Current flowing here is I1, here is I2. Both are in same direction. Now what the observation is, that if the current is in same direction, both the wires will experience an attractive force towards each other. Alright. So this wire will be attracted by this wire and this wire will be attracted by this wire. So here let's say this is force on 1 due to 2. This will be force on 2 due to 1. Newton's third law, action reaction pair. So here basically F12 is equal to F21, the magnitude if I talk about. Clear? If two wires in which current is flowing are kept at some separation, then these two wires will experience force. Now depending on the direction of current, it will be decided whether it will be an attractive force or a repulsive force. If the direction of current is same in both the wires, it will be an attractive force. Clear? Attractive force. And if the direction of current is opposite, then what will happen? It will be a repulsive force. Force on 2 due to 1. Force on 1 due to 2. Clear? Let's say this is wire 1, this is wire 2. Here also, this is wire 1, this is wire 2. Just the name of the wires. Alright. Here again F12 will be equal to F21. This is attractive force, this is repulsive force since the direction of current is opposite. Now, note it down. Let's find the value of this force. How much is the value? So now these two wires are there, current I1, I2. Again, let me name this as wire 1, name this as wire 2. Current I1, I2, and they are kept at a separation D, and both are infinitely long wires. Just now we have seen that if the current is in same direction, they will be attracted towards each other. But now let's understand it logically. Okay, these were the observations. Now here, we'll try to get this from the logic. See here. This is a wire due to this wire. Why? First of all, why these wires are experiencing force? There should be something which should give it force, right? Now we have studied that if there is a wire in which current is flowing, that wire will produce a magnetic field around it. Remember? Magnetic field due to an infinite straight current carrying wire, mu naught I upon 2 pi into D or A. What the formula what you have studied was A, correct? Where A is the perpendicular distance from this wire. Remember? So now this wire is actually producing a magnetic field. So at a distance D, if I want to see the magnetic field due to this wire at a distance D, that means here in this region where this wire is kept, This is producing the magnetic field in the region where this wire is kept, and the direction of magnetic field will be, keep your thumb in the direction of current, then the curl will give you the direction of magnetic field. So here magnetic field is inwards, right? So magnetic field is inwards. So this was one thing, that if a current carrying conductor is there, it will produce magnetic field around it. So around this it has created a magnetic field at a distance d, let's say. One more thing what we have studied is, if a current carrying conductor is present in a magnetic field, it experiences force. Remember that force was F is equal to I B L sine theta. Or vector wise, if you want to write, F vector is equal to I L vector cross B vector, correct? I hope you remember this. So now see, basically direction we will see from right hand rule. So we have to see this particular formula, IBL sine theta. Okay. Now this conductor is kept in a magnetic field. It will experience a force. What will be the direction of that force? What will be the direction of that force? If we want to find the direction, what do we used to do? Fingers in the direction of magnetic field, thumb in the direction of current, then the palm gives the direction of force, right? Fingers in the direction of magnetic field, thumb in the direction of current, then the palm gives the direction of force. So here the force is in this direction. This will be the force on this wire due to 1. Why due to 1? Because the force is due to the magnetic field produced by 1. If I remove this wire, there will be no magnetic field here. So basically it is experiencing force because of this. Clear? Now we got to know the direction. Let us find the value. F21, that is equal to IBL sine theta, where I is the current flowing in the conductor, that is I2, and B is the magnetic field, external magnetic field, right? So external magnetic field is this, which is produced by this wire. So let's say this is B1. I am naming this magnetic field as B1 because this magnetic field is due to this. All right. So here B1 L. Now see this L, if you see, L is the length of this conductor. It's an infinite wire, correct? So I cannot take out the length, the force on complete wire, because if I see L is infinite. If I put L as infinity, F will be infinity, right? So the force on this complete wire we cannot take out, but still I am writing L here. We will be finding out force per unit length. All right, in a unit length, how much force is there, that we'll find out. Sine theta. Sine theta. Now here if you see, what is theta? Angle between L and B, right? L vector, if you remember, the direction of L vector was same as the direction of current. So here L vector will be upwards. This will be L vector. And force, sorry, magnetic field. L and B, the angle between length and magnetic field. So magnetic field is inside. Now L is this, magnetic field is this. What is the angle between L and B? 90 degrees, correct? L is this, magnetic field is inside. It is 90 degrees. So this will be sine 90 degrees. So that is I2 B1 into L. That is what F21 is. Now as I told, since this is an infinite wire, the length is infinite, we cannot find out force on complete wire. We will be finding force per unit length. On a unit length, how much force is there, that we will find out. That means if I divide L, this force per unit length is equal to I2 into B1, correct? F21, here see I2 B1, remember this way. Now what is this B1? Current will be given I1 I2 and the separation will be given, that is D. Can you write the formula for B1? B1 is the magnetic field due to this wire, that is this, right? So B1 is equal to mu naught I1, because the magnetic field is due to this wire, divide by 2 pi into the perpendicular distance. If at this point I am finding out the perpendicular distance is D. This is the magnetic field due to 1. magnetic field due to infinite current carrying wire at a point which is at a separation d from it. This is the magnetic field. Mu naught. I told you, remember this formula. रात के 2 बजे भी ये formula याद होना चाहिए. That important formula this was, right? Mu naught I1 upon 2 pi d. Substitute it there. On substituting it here, what we'll get is I2 into mu naught I1 divided by 2 pi d. That is the force per unit length. So force on 2 due to 1 per unit length is equal to mu naught I1 I2 upon 2 pi d. Again, this formula is very important from board's point of view. You will definitely get a question from this. All right, mu naught I1 I2 upon 2 pi d. Very easy to learn it. Mu naught upon 2 pi will be the constant, and then the product of the current divided by the separation. Product of the current divided by the separation. Some people learn the same formula like this. F21 per unit length is equal to mu naught upon 4 pi 2 I1 I2 by d. Clear? Why? Because mu naught by 4 pi, they remember this as a constant. Clear? Mu naught by 4 pi, they remember this complete as a constant. So then they'll remember 2 I1 I2 by d. So either you can remember this way or you can remember this way. Both are same only. Clear? I would recommend this. This is easy. Mu naught I1 I2 upon 2 pi d. Clear? Now, this is force 2 due to 1. Now what will be force on 1 due to 2? Action reaction, both will be same. Okay? If you want, I can derive for force on 1 due to 2 also. Or you will try it on yourself. Let me do it. Fine. Force on 2 due to 1 is equal to, now this force will be due to the magnetic field produced by this wire. Now this wire will be producing a magnetic field at this area, this region. What will be the magnetic field? Sorry. What will be the direction of magnetic field first of all? Thumb in the direction of current and curl the fingers in the curl will give you the direction of magnetic field. So here magnetic field is outwards basically. If you see, the magnetic field here is outwards. Clear? The force that this wire will be experiencing, because now this conductor is there in a magnetic field, a uniform magnetic field. Okay? So the force which is, the direction of force which it is experiencing is fingers in the direction of magnetic field, thumb in the direction of current, palm gives the direction of force, that is inwards. See, F12. All right. So everything is correct. Direction and all is set. Now we have to find the magnitude. Force on 1 due to 2 will be IBL again. IBL, where I is the current in the conductor. B is the external magnetic field. Here external magnetic field is due to wire 2. So I'll write this as B2. Okay. So this will be B2 into L IBL sine theta, that is sine again 90 degrees, correct? Angle between L and B, L is in the direction of current, B is outwards. See, 90 degrees it is. Alright. So this will be I1 B2 L. If I want to write force, this is force on 1 due to 2. So force on 1 due to 2 per unit length will be I1 into B2. Now what will be B2? Magnetic field due to an infinite current carrying conductor at a distance d. Mu naught I2 upon 2 pi d. So here I1 is there, here mu naught I2 upon 2 pi d, that is mu naught I1 I2 upon 2 pi d, that is force on 1 due to 2 per unit length. Clear? See, both the formulas are same. Mu naught I1 I2 upon 2 pi d, mu naught I1 I2 upon 2 pi d. So whether you see force on that wire or this wire, both the wires it will be same. Alright, note it down. Next, definition of ampere. Definition of ampere. So how do we write the definition of ampere? Basically what this is, suppose there are two current carrying wires kept at separation D. Alright. Now see, first of all, this force what we have calculated is a very small force. Because if the value of this force will be very high, you would have, we have never seen that two wires kept there and they got attracted to each other, right? We have never experienced this on seeing them. They never stick to each other, correct? Why? Because the value of this force is very, very small. If let's say two wires are kept on table, right? In both the wires the current is flowing. No doubt, if the current is in same direction, there will be force of attraction. If in opposite direction, there will be force on repulsion. But we have never seen them moving close to each other or moving away from each other. Why? Because the force is very small. Maybe the force of friction would become equal to that, because of which they just stay like that. Clear? So this force is very small. So what is the definition of an ampere? If two current carrying wires are there, in which current flowing is I1 and I2 kept at a separation D. Now suppose if I1 is equal to I2 is equal to 1 ampere. If I give the current to both the wires as 1 ampere and if I keep them at 1 meters away, current on both the wires is 1 ampere, they are kept at a separation of 1 meter. Now if I calculate the force per unit length, force per unit length will be mu naught I1 I2 upon 2 pi d, correct? So that is equal to mu naught I1 is 1 ampere, I2 is 1 ampere, 2 pi into d is 1 meter. That is mu naught upon 2 pi. What is the value of mu naught upon 2 pi? If you remember, I told mu naught upon 4 pi is 10 power minus 7, correct? So this is basically 2 times mu naught upon 4 pi. That means 2 into 10 power minus 7, 2 into 10 power minus 7 Newton per meter. That is the force per unit length. If the current on both the wires is 1 ampere and they are kept at a separation of 1 meter. So this is the definition of 1 ampere basically. What they say in your books, it will be written 1 ampere is that amount of current. 1 ampere is that amount of current which when flows in two wires kept parallelly at a separation of 1 meter, then 1 ampere is that amount of current which when flows in two wires kept parallelly at a separation of 1 meter, then the force per unit length is 2 into 10 power minus 7 meters. Clear? 1 ampere is that amount of current which when flows in two wires kept parallelly at a separation of 1 meter, then force per unit length is 2 into 10 power minus 7 meters. Right? Note it down. This is the concept basically. If you get a better definition in word, learn that. But this is the concept basically. Okay? Just check the grammar and all those things and then write in exam. Clear? Now next, find net force per unit length of on wire Q. So this is one question what I've kept to make you understand the concept better. So here, find net force per unit length on wire Q. Wire Q is this. On this wire I have to find force per unit length. Now this wire will experience force due to both the wire. This wire will be producing a magnetic field. This wire also will be producing a magnetic field. So magnetic field due to this wire at this I have to find out. Magnetic field due to this wire at this area we have to find out. Then we have to take the net magnetic field, and then force on this is F is equal to I into B net into L sine theta. Clear? Let's see. Current is 3 ampere. The distance is 1 meter. So magnetic field due to this wire at this point. If I see the direction, thumb in the direction of wire, curl will give the direction of magnetic field, that is inwards. So this is BP, correct? B due to R. So now thumb in the direction of current, then the curl will give the direction of magnetic field, that is outwards. Outwards. This is BQ. Now you see, one magnetic field at this region is going inside and one magnetic field is coming outside. That means B net will be the difference between BP and BQ. We don't know which one is bigger, which one is smaller, right? Magnitude, if I say, it will be the difference of BP and BQ. But now from common sense, I can understand one thing, that BP and BQ will be same. Why? See, the current is 3 ampere, current is 3 ampere, and we are taking out magnetic field at a separation of 1 meter from this wire also, at a separation of 1 meter from this wire also. Right? So BP, BQ will be same, B net will be 0. If B net is 0, force on this is I into B net into L. B net is 0, force on this is 0. From common sense, even you don't have to use pen also for this question. But still, if you want, I'll take out. Let's say BP is equal to mu naught into 3, mu naught I upon 2 pi d, right? Into 3 upon 2 pi into d is 1 meter. BQ is equal to mu naught into I upon 2 pi into the separation. This is inwards, this is outwards. See, the value is same. Current is same, separation is same. Current is same, separation is same. Correct? So if I subtract these two, B net will be BP minus BQ, that is equal to 0. Force on Q is equal to I on Q into B net into L. Right? Sine theta will be sine 90. So this is I is 3 into 0 into L, and that is 0. Force per unit length, if you want to write, force per unit length, if you want to write, remove this L, 0. Clear? Easy question. All right. Everything depends on how much magnetic field comes at that particular region. Now let's see the next part, that is torque on rectangular loop in a uniform magnetic field. Torque on rectangular loop in a uniform magnetic field. Now before this, one small concept I'll tell you, which we'll discuss in detail in the next session, but it will be used here, that's why I'm telling you, okay? Suppose there is a rectangular loop, okay? The current flowing is like this. Let's say the current flowing is I, alright? This side, let's say, is A, this side, let's say, is B. It's a rectangular loop. So let's say the length is B, the breadth is A. Clear? Now, in the next session, we'll be seeing this properly, that any current carrying loop behaves as a magnetic dipole. Current carrying loop behaves as a magnetic dipole. So if this behaves as a magnetic dipole, that means it will be having a magnetic moment also. So the magnetic moment of this particular loop will be I into area vector. Clear? Magnetic moment. Magnetic moment. Clear? What is the direction of magnetic moment? From the formula you can understand the direction of magnetic moment will be same as the direction of area vector, right? But no doubt area vector is perpendicular to this particular loop, right? But the direction of area vector is not defined. It can be this side also, it can be that side also, right? So how to know the direction of magnetic moment? curl your fingers in the direction of the loop, right? In the direction of current in the loop, then the thumb will give you the direction of magnetic moment. So here in this case, magnetic moment is inside. Here in this case, magnetic moment is inside. If current was anti-clockwise, magnetic moment would have been outside. Clear? In the next session, we'll be discussing it properly. So if it is behaving as a magnetic dipole, that means one side will be south, one side will be north. Again, in 10th standard only we had discussed, right? If you remember, this is clockwise. If I make S, see this face will be south. From the opposite side, if I say the current, see if the current will be anti-clockwise. Anti-clockwise means north pole, right? So again, we'll be seeing properly, don't worry about it. But for this session, what you have to remember, what you have to keep in mind is M vector is I into A vector. Clear? Because this will come in the formula for torque. Now let's see, there is a magnetic field. In this magnetic field, there is a rectangular loop. Now this is a current carrying loop. So let's say the current is flowing like this. This side, let's say, is A, or I'll write inside. This side, let's say it's A. This side, let's say it is B. Clear? Now, will this particular loop experience force? For the force on this entire loop, let's take out force on each part of this loop. Here, if you see, this is a straight wire. We know that if a straight current carrying conductor is in a magnetic field, it experiences force. So this wire will experience force. This wire is also in magnetic field, it will experience force. This wire is also in magnetic field, it will experience force, and this wire will also experience force. All the four wires will experience force. Then we will see the net force on this entire loop. All right. Now the force on this side. What will be the direction of force? Again, right hand. Fingers in the direction of magnetic field, thumb in the direction of current, fingers in the direction of magnetic field, that is inside, thumb in the direction of current, that is downwards. So the palm gives the direction of force, outwards. So here the force will be outwards. Can you tell me the value of this force? What will be the value of this force? This force is equal to I. Let's say the current flowing is I into B, the magnetic field, let's say, is B. All right. Into L, what is the length? B. For this wire, the length is B. Sin theta, angle between this length vector and magnetic field. 90 degrees. So sin 90 is anyways 1. So IB into B. Let's say this is force 1. Here on this wire, force will be fingers in the direction of magnetic field, thumb in the direction of current, downwards. So on this complete wire, the force is downwards. That is, let's say F2, that is equal to I into magnetic field into the length of this wire, IBL, that is A. Correct? It's a rectangular loop. Whatever length is this, the same length is this. Here, the force will be fingers in the direction of magnetic field, thumb in the direction of current. Again, outwards. See my palm, right? F3, let's say. I, B into B. Here, fingers in the direction of magnetic field, thumb in the direction of current, upwards. So here, the force is upwards, that is F4, let's say. That is I into B into L, that is A. Correct? Now, we got the force individually on each straight wire. Now, on this entire loop, if you see F net, what is F net? I'll write F net here. What is F net? This force is upwards, IBA. This force is downwards, IBA. they will cancel each other. The magnitude is same, the direction is opposite. This force IBB is this side, this force IBB is this side. Magnitude is same but the direction is opposite. Again they will cancel each other. That means net force on this entire loop is 0. So from here what we understood is, if a rectangular loop is kept in a uniform magnetic field, the net force on that loop is 0. Clear? Now, I hope you understood this. It was easy to understand, right? Now, what about torque? What about torque? If you see torque net is also 0. Because here, these both forces, the line of action is same. If you see, if I take it as a paper, if I put pressure, if I put force outwards on the paper like this, there is a paper, if I put force on outwards like this, nothing will happen, it will not rotate. Torque means rotational force, right? From here upwards and downwards, if I pull it, it will not rotate, right? Because this force is basically all the forces are outwards. It is stretching that paper. If I'm having a paper or a book, something, I don't have right now here, otherwise I would have shown. All right. So here, due to which torque net is also 0. Common sense, understand it properly. Take a paper, put force from both the sides, same, it will not rotate. Put force from both the sides, same, it will not rotate. Right? It is a stretching force. Clear? Note it down. So here basically, what is the main thing is why I told you this M vector. For this loop, what is the direction of M vector? Inside. M is inside, B is also inside. So basically here, M vector is parallel to B vector. Or you can say, in this case, angle between M vector and B vector is 0 degrees. This is the main thing. So if angle between M vector and B vector is 0, then F net is 0 and tau net is 0. Remember this, very important. If angle between M vector and B vector is 0, F net is 0 and tau net is 0. If this is there, then this. I'll make it properly. Clear? Note down. Now, if there is any angle between M vector and B vector, let's see that case. So now if the loop is rotated by angle theta, so if it is rotated by angle theta, this means if angle between M vector and B vector is theta, it means the same. How? I'll show you. See, earlier, this is the magnetic field we know. Inside. Earlier our loop was kept like this. Now our loop is rotated by angle theta. If you see, this angle will be theta. The loop was like this, I have rotated it by theta. Clear? Current was flowing like this. The same loop it is. I have just rotated it. Okay. This is still A, this is still B, same loop it is. Now see, what is the direction of magnetic moment? Curl the fingers in the direction of the current in the loop, then thumb will give the direction of magnetic moment. This time magnetic moment is not like this. It is not like this, it is like this. See, perpendicular to this loop, if you see, it will be, earlier M was like this. Now if this loop is rotated by theta, this M will also be rotated by theta. Earlier it was like this, now it will be like this. See, perpendicularly if I see to this plane, it has to go this side. That means M vector will be From here, if you see, m vector will be somewhat like this. From here, it is also rotated by angle theta. Got the point? So if our loop is rotated by theta, m will also be rotated by theta. Common sense. Correct? So that means now m is like this, b is like this. Still, see, the angle is theta. B was earlier also like this, m was like this. Both were having zero angle. Now m is rotated like this. So if you see the angle, theta angle will come here. All right. So angle between m and b is theta. So if this is the case, again let us find the force on each straight wire. On this wire, F1, let's say, how much it will be? How much it will be? I into B into L is B sine theta. Again, if you see sine theta, angle between B and B means angle between this length vector and B. So this length vector is still in the direction of current, that is downwards. B is inside. Angle is still 90 degrees. No doubt it is rotated, but angle between this wire is still 90 degrees, so it will be IBB. Here also, if you see F3, let's say, that is again current is I, magnetic field is B, this length is B, and angle again, since it's a straight wire, current is going upwards, magnetic field is inside, 90 degrees. So sine 90 is 1, IBB. F1 is still equal to F3. So I'll just write it as FF. Clear? Now here there will be one force upwards, F dash, let's say. The same force will be there downwards, F dash. Right now we cannot write it as IB into A. In some books it will be written IB into A. No, it's not IB into A. This is rotated by angle theta. Earlier, this current was like this, B was like this. It was angle 90 degrees, correct? But right now, this B is like this. So, sine theta will also come into the picture. Okay? But, so here it will be I into B into A sine theta. I, B, A sine theta. Here also the same thing. I, B, A sine theta. Easily we can understand both the forces are equal. Both the forces are equal. Now, what will be F net? F net. This force upward, this force downward, both are equal. This force IBB, this force IBB, both are equal. F net is 0. F net is 0. Clear? Now what about tau net? This time, do you think torque will also be 0? Do you think torque will also be 0? No. Why? Because the line of action of this force and the line of action of this force are not same. Here this force, if I just make it more straight, if I stretch it, this force is basically upwards, right, above it, and this force is behind the line of action if I talk about, correct? So now if you see, this paper is actually, it was like this, now it is rotated. Now if I put a force on this side of the paper, this side, and this side of the paper, this side, it will rotate, correct? I'll show you, one second. See, this is a book. Earlier it was kept like this. Let's say earlier the rectangular loop was kept like this. If I stretch it from both the sides, nothing will happen. If I stretch it from here also, nothing will happen. But now if I rotate it by some angle, okay, now it is rotated. Now if I put a force here and I put a force here, it will rotate, see. This force, I am pulling it like this. From here, I am pulling it like this. It will rotate. Torque is there. Rotational force is there. Clear? Another way to understand, the line of force of action is not same. Here the force is this. If I extend this line, it is actually this side, right? This force, if I extend this line, it is this side. So here the line of force is this. Here the line of force is this. Both are not straight. But here top and bottom, if you see, From top and bottom, if you see, the line of action of force is same. This is upward, this is downward. The line of action of force is same. Clear? Same straight line. But here it is not straight. Here it is this side, right? Here it is this side. Got the point? Easy to understand. All right. So here there will be the torque net, tau net is not equal to 0. Torque net is not equal to 0. If you want, you can write the reason also, because the line of action of force is not same. Let us understand it. Let us see the top view of this. If you see the top view, it will be something like this. This is B only. These lines are B. This is the rectangular loop only. Now I am seeing it from the top. Magnetic field line is going like this inside, and the rectangular loop is here. If I see from the top, I will be seeing magnetic field lines going upwards, right? And this is a straight rod. It will be seen like a rod only if you see from the top, right? So that is the top view what I have made. So earlier my rectangular loop was like this. Now it is rotated by angle theta. Force, if you see this force, see this force will be this side, F is equal to IB into B. This force is this side, that is IB into B. Correct? These two forces. From top, if I see, these forces will look like this only. Correct? These two forces will cancel out each other. These two forces are on this axis. Let's say this is the axle of rotation. This is the axle or axis of rotation, okay? Here. So these two forces are on this axis only. So they are not creating torque, and anyways they are equal and opposite, so they will cancel each other. Clear? Now because of this, obviously if I pull it like this, a rotation will happen. A rotation will happen. So because of this, torque net is not 0. Clear? Now this I have told you to write the value of this torque. We know that what we got to know from here, if M vector and B vector are at some angle theta, F net is equal to 0, but tau net is not equal to 0. Correct? The value of this tau net will be, what is torque? Force into the perpendicular distance. That perpendicular distance is from the axis of rotation, right? So this is the force. See the line of action. This I was telling. This line of action is this. This line of action is this. Both are not same. From here, perpendicular distance between this, the line of action of this force and this axis, this distance, from here, this distance. Correct? So torque will be this torque plus this torque. Torque is a vector quantity, right? If the direction of the torque will be same, we will be adding it. Now see, this torque is actually rotating this rod clockwise. From here, if you see, it's like a rod only, that's why I'm telling rod. It is rotating it clockwise. Here also, if you see, this force is also rotating it clockwise. This force is taking it this side. This force is taking it this side. So basically, both the torques are supporting each other. So torque will be added. Torque will be added means force into perpendicular distance plus force into perpendicular distance. So that is 2 times force into perpendicular distance. That is 2 into force is I into B into B. What is the perpendicular distance? This distance. Now this length. What is this length? This one, A. From top we are seeing. Correct? So this is A. This entire thing is A. If this is A, that means this is A by 2. This is also A by 2. So if this is a by 2, what is this? This is theta. See, this is theta. This is a by 2. So this distance will be a by 2 sine theta. This will also be a by 2 sine theta. Here also this will be a by 2 sine theta. Just check. If this is theta, this is also theta. That means this perpendicular distance will be a by 2 sine theta, the same as this distance. A by 2 sine theta. So this will be 2 into I b into b into perpendicular distance is a by 2 sine theta. Now see, this 2 and 2 are cancelled. I into b into ab, or I can write it as IAB into b. What is this a into b? This is the area of this rectangular loop, right? So this is I into a into b, that is torque net. That is torque net. Clear? Sorry, sine theta is also there. Sine theta is also there. I A B sine theta. Very very important. Again, रात के 2 बजे भी ये फॉर्मूला याद होना चाहिए. I A B sine theta. Now, I told you initially in the starting, what is IA? M, magnetic moment. So from here I can write torque net is equal to MB sine theta. And we know M is also a vector quantity, B is also a vector quantity. So after the multiplication of this vector quantity, a sine theta is there. Can I write it as cross product, M cross B? Correct. So here I can write it as torque net is equal to M vector cross B vector. Some people will think, why not B cross M? Why not B cross M? Because M cross B will give the direction, will give the correct direction of torque. See, direction of torque is, if you remember, direction of torque was R cross F. R cross F. Here, R vector will be this, R means the length. Here, R vector will be this outside, and this is the F vector. So if I do R cross F, my thumb is going inside. R cross F, my thumb is going inside. Clear? Arey bhai. See, understand. This will be R, the length of the rod here. From top, if you see, it looks like rod only. So this R will be like this. R vector. F vector is this. Now see, R cross F. R cross F. My thumb is going inside. R cross F. Right? Here also, if you see, R cross F. R is this. Here. R is this. F is this. R cross F. Again, my thumb is going inside. Both the times, torque direction was same. That's why we added first thing here. Alright. Second, the direction of torque is inside. Due to this also inside, due to this also inside, total torque is inwards. Correct? Just do M cross B. M vector we know from here. See, M vector we know it is in this direction. From top, if you see, it is in this direction. Right? This is the loop. M vector will be in this direction, perpendicular. Area vector, perpendicular. Right? The direction of area vector is same as the direction of magnetic moment. Here, actually the loop is like this, correct? We are seeing the top view. So perpendicular will be perpendicular to this, perpendicular to this. This is B. See, B vector and M vector is having angle theta. That's what is written. This is B. Now M cross B. M cross B. This is M, this is B. M cross B. My thumb is coming inside. Clear? M cross B, if you do, this is M. This line is B. M cross B, if you do, my thumb is coming inside. So the direction of same, if I do B cross M, thumb will be outwards. It will not match the direction of torque. So that is why it is M cross B. Clear? Alright, note it down. Very important. Done. Next. Now see one more thing here. If you remember this, if you remember electrostatics, just a small recap, or I'll just write in electrostatics. Clear? If you remember the formula for torque, P vector cross E vector, correct? Electric dipole into electric field, electric dipole cross electric field. The same way you can remember, here electric dipole was there first, then electric field was there. The same way here magnetic dipole is first, then magnetic field is there. Clear? Both the formulas, why I am telling you right now, so that you can relate and you will not forget. Got the point? Okay. Now if I talk about the maximum torque and the minimum torque, let's see. Torque maximum. For maximum torque, from this formula mb sin theta, for torque maximum, this theta should be 90 degrees, sin theta should be 1, right? So if theta should be 90 degrees, that means sin theta will be equal to sin 90 will be equal to 1. That means tau max is equal to mb or IAB. Clear? I'll write IAB. IAB, or that is equal to mb. For torque minimum, minimum torque is 0, right? So this will be theta should be 0 degrees. So sin 0 will be 0. So torque minimum is 0. Torque minimum will come when theta is 0 degrees or 180 degrees. When theta is 0 degrees or 180 degrees, and maximum torque will come when theta is 90 degrees, perpendicular. Now theta 90, what does it mean? Theta 90, what does it mean? M vector is perpendicular to B vector for maximum torque. Clear? Very important. For maximum torque, M vector should be perpendicular to B vector. Here, M vector is parallel to B vector, or M vector is parallel to minus B vector. Very simple, correct? This means anti-parallel basically. So here, this entire thing is for minimum torque. Note down. Done? All right. Now, next. If let's say n turns are there in the loop, if n turns are there in the loop, here what we have seen is for one turn. This loop is having only one turn. But now if n number of turns are there, very simple, the current will become n times. If the current becomes n, rest everything will be same. Area will be same. Magnetic field is the external magnetic field, that will be same, right? Only current will be changed. So here torque will be equal to n times IAB sin theta. Clear? Everything is same, only the current became n times, Ni. Done. You can also write it as, now this NIA is M. This formula is same because now this NIA is magnetic moment. This NIA will be the magnetic moment. Clear? So this will remain the same, that is M vector cross B vector. Here this is tau vector. This is same. But what you have to remember is this. NIAB sin theta. Clear? Easy today's lecture was. I hope you understood everything properly. Just revise this lecture again. Okay? Try to understand how we got the value of the torque. Try to derive it on your own. All right, in the next session, we'll be doing circular loop as a magnetic dipole. What I told, loop as a dipole, we'll be seeing in detail in the next session. In this session, we only see a glimpse of it. That is M is equal to I into area vector, correct? All right, I hope you liked today's session. I hope you understood today's session. If you liked it, do press the like button. Share it with your other friends who are preparing for their boards and competition. Subscribe to our channel and do not forget to click on the bell icon so that you never miss any update from us. All right. Do visit our website www.v-learning.in. All these live sessions you will be getting there. Along with that, you will be getting lecture notes in PDF format. You can download them, you can learn from them. Okay, do check it out. We'll meet up in the next session. Till then, keep learning from V Learning. All the best.